Hello everyone, welcome again to today's General Interest Seminar. My name is Jamie Hu. I'm a Chocolate HPC consultant and also part of Computer Canada. So today I'm going to introduce the parallel approaches in the HPC programming language Chapel. We talked about the Chapel-based language basically is an overview previously. Is recorded. And if you are interested, you can go to the search Chocolate YouTube channel and you can find it. So when we actually introduce the parallel approaches like the commands, the statements. So I will try to use the example code to illustrate those concepts. So the example code are available on Gram under my home directory /home/jamiehu/chapel. I may do a bit of demo if we have time, and if not, and because the majority of the code are already on the slides, and I think it may not necessary to do the demo. Okay. So Chapel is a productive parallel programming language developed by Cray. It is portable and scalable, and is open source and cooperative. So it's a group of people and organization and put some efforts to it and still on the developing. So what we have on our cluster is an old version now, and there is a new Chapel version released, and we hope someday we'll bring that new version our systems. So Chapel is designed around a high-level abstraction and multi-resolution philosophies. So in the following some slides, and I'll try to bring it up and to show that multi-solution structure. So based on the design and the structure, users can incrementally add more details to the original code prototypes. So let's make the software is more flexible. So the goals, as with some other HPC languages, and this group of them, so it basically supports general parallel programming, and it says any parallel algorithms and on any parallel hardware. So we know, and so far the dominant approach for parallel programming is the MPI for distributed memory parallel solution, and then is the OpenMP for the shared memory parallel solutions. So those two are library or compiler directive, where is very good, and you can use it in C or in Fortran or C++. So that's still a dominant thing. So there's some time now. There's a bunch of new languages proposed, the so-called HPC languages. So what's the goal there is basically want to make parallel programming at scale far more productive, and in a natural way is implemented in the language itself, and it doesn't need to go to the other road like to build to use the MPI type of libraries. So all those HPC languages is a family of the partitioned global address-based languages. So Chapel is one of them. So the PGAS is a program model suited for shared and distributed memory parallel machines. So on the top abstract definitions, and PGAS support a shared namespace on distributed memory. So that permit parallel tasks to access remote variables by naming them. So that's the key and for all kinds of the so-called HPC languages. In the meantime, it established a strong sense of ownership. So every variable has a well-defined location, and the local variables are cheaper to access than remote ones. So the traditional PGAS language has been HPMD in nature. So the best known examples are Fortran Core Array and the UPC. These two languages still under developing as well. And a few others, and they actually stopped. I guess, not many interested in it, and or maybe the funding agency stopped funding it. So Chopper is a PGAS, but unlike most, it's not inherently HPMD. So it's not, don't think it is another copy of the program. So it's as like the traditional languages, global name and address space comes from lexical scoping, and each declaration yield one variables. And the variables are stored on a local where the task clearing it is executed. And the communications are implicit, so user can reason about the communications. So semantic model is explicit about where data is placed and the task is executed. Execution time queries support reasoning about the localities. So the code won't say the sum, you can say here or there, and you can find the ways the variables and how to call it. So it's a compiler language. Chapel is a compiled language, and Chapel source code must be compiled to generate a binary or executable to be run on the computer. So that's because Chapel comes with some built-in variables and the high-level system resources. So that is actually available in a compiler and runtime as well. So the Chapel source code must be written in text files with the extension .chpl. So the command is chpl. So here it's very simple. It's say hello.chpl and just the two lines. So one is print hello world, and then another print whatever is print line. So once you have Chapel installed on your systems, and then you have the Chapel source code. So you compare it and use chpl, and you name a binary and the source code. So just like you compare code like in C or in Fortran. And then the compiler comes with some options like the optimizations. You can add dash fast to it. So dash fast indicates the compiler to optimize the binary to run as fast as possible in a given architecture. So here we have checked our clusters. So we can compare it and we'll run it. And this is basically will give the results. Certainly this is a sequential code. It's a very simple one. And then I can spend a little bit of time to explain it available on our clusters, on Computer Canada clusters. So the same version, the similar structure on the clusters Theta and Gram. There's two different versions here. So because the latch of Chapel, and there's one version is called Chapel-single. It's for to run code use the CPUs on one single load. So you can imagine, you understand this is sort of like the shared memory solutions. And then the other one is for code run crossload. So for multiple load. So we come with a long name. It's chapel-slam gets that run underscore IBV. So when compare the chapel for Crossload, or it closely related to the network into the structure of a cluster. So different cluster may have different configurations to it. So if you want to, because it's built on the CFMFS and it's all modularized. So to know what's available on the cluster, as usual, use module spider and module spider chapel. And you can find the dependency. And the chapel was built using the GCC compiler. So the first thing, you need to merge node to the GCC to replace the default internal compiler on the cluster. And then you can merge node the chapel. So once you have it, and you can find where the build is, and then you compare it, and then it's ready to go. However, for the starter, and if you want to try it, and for all, the example I used today is for testing only. So for testing jobs, you would like to run in interactive mode. So you use S a lot to request a computer resource and for interactive job. So here is for the one CPU. So S a lot, basically you need to specify the time and how long you need to use and the number of CPUs in this case and the memory. And then you count and then you can write. And for the parallel run is basically two things and two type of reservations. So for example, here I reserve 4 CPUs and on one node. So this will enable me to actually run the test, the parallel chapel code using the single node build. It's essentially run the same as the shared memory parallel code. And the other one you can, as a lot, you can actually say, ask for 2 nodes, and each node will have 2 CPUs. And in this case, is basically, we can test the chapel code run Crossload. Okay. And in the future, if happen you have real chapel code for productive jobs, and certainly you will go as required, and you create .sh script and put all the computer, all the module node things to it, and you submit job to a queue, use SBatch. So everyone, as long as you know how to use a cluster, you will know that there's nothing different. Okay. So as usual, when we talk about parallel computing or parallel programming, there's a few things, few terms that will come up with. So one is the task. So the task in Java we talk about is the concurrent task. So it's a unit of computation that can or should execute in parallel with other tasks. So task pretty much is independent to each other. It's concurrent concurrent task. So it should be straightforward. And then it's thread, and the thread is, when we run threaded code or pthread or OpenP code, it actually uses, it runs in thread. So task runs on thread. So it's a system resource that executes tasks. It's not exposed in a language. So occasionally exposed in the implications. So it's actually when you run code, you're writing code, is a task parallelism or data parallelism is come up with, but it's, you will use all of them in a real applications. So task parallelism is a style of parallel programming in which parallelism is driven by program-specific tasks. In contrast, data parallelism is a style of parallel programming in which parallelism is driven by computation over connection of data element or their indices. So Chapter will come with different statement to do the task parallelism and data parallelism, and certainly they will do both some of them. Okay. So here basically is a whole slide I took from Chapter's website. So to demo and to basically to explain Chapter's multi-solution philosophy. And this diagram basically gave different layers. Certain layer, each other, they will arbitrarily or interact with each other. So it's called a multi-solution design, support a multi-tier of features. So the high-level programmability and the productivity, and the low level is for greater degree of controls. So build the high-level concept. So in terms of lower, so it's basically permit the user to intermix layer arbitrarily, like domain maps data parallelism. Okay. So the first concept come in chapter is the localers. So the definition of the localers is abstract unit of talked architecture, and it supports reasoning about locality, and it can define here and there, and like the number of tasks or some variables you can trace it. So it's basically here there is say is a local, is variable is local, or is variable is remote, and it's capable of running tasks and storing variables. So it has processes and memories. So if we talk about hardware, it's basically here we talk and the localers in chapter is basically the computer load. If you give it a whole load or whatever, how many CPUs you reserved. So that's the whole thing. Is a computer node or is a multi-core processor or SMP. So thereafter, when we talk about locals, it's called about a bunch of CPUs on single load. Okay. And then because we say Chapel certainly can run jobs cross-load, so it can use multiple localers. So how to run a code on multiple localers, and its user has to specify how many locals to use when you run your code. So when you have a binary, and then in the run command you add either dash number localers equals 4, say I have 4 localers. So what does it mean is say you have CPUs and CPU across 4 loads, okay? Or you can use say add dash in L and space 4. So that's because you run your code across 4 loads or 4 locals. So Chapel provide building local variables. So it's actually is a config constants. So for example, if we use 4, and you will have locals will have error 0, error 1, error 2, error 3. And the main code Chapel always started, and the code on the local is numbered 0, and the Chapel always started with run once the main code will run one thread on the local 0. Okay. Now we come and say what's the way for the chamber to do parallel. The first thing come is the central part is for the statement is for all loops. So this is the central concept for data parallelism. So this small piece of code here, for example, you can see this code, you understand it. So we have variable define variable counter. And because the structure of the for loop in Chapel is like the for loop in Python, it's loop over a range. So the for loop structure is something like this. And the for all is basically change the for loop to be for all. And then here, if we use reduce, and reduce is a functionality implemented in Chapel. It's just like the reduce implemented in OpenMP, those type of thing. So it will allow you to do sum, find the maximum, find the minimum, those type of things. And also it will avoid the race conditions, something like that. When you do when you do data some things, and then this will work, and you find you compare it, you can run it, you can find the sum, and you run. Certainly, this is run on multiple CPUs. So it's just this loop parallelism is just can be as simple as this. So when you use for loop, it's basically when use one loop should be executed in parallel, but it can, well, this code certainly can run in sequentially, there's no doubt. And when you use the Z is basically a number of tasks. It's less to the number of iterations, and typically the task is more than one or less than the iterations. So this is one for command common with is for all. And then Chapel has another called call for all loop. Call for all loop is basically is create a new task per iteration and execute user task per iterations. So this is basically want to do a loop and parallelization, and when you use it when the task and its number of tasks is equal to number of iterations. That means basically means your loop each iteration has a substantial work to do. So here is a simple code to show the command will work, and say it's basically the number of tasks get the say how many CPUs we reserved, and it can call here that number of PUs will get the number of how many CPUs and we're actually using. So this is here is a common built-in variable there. And then you can say call for all, and the run from all the way go to the number of tasks, and you can say what each task do what. So if you compare this code, you can run it. In my case, pretty much as I showed, I reserved 4 CPUs on one node. So it's all the number of CPUs are 4, and each were the tasks from here, the range from 0 to 3. So they have 2 ways and to do the loop parallelism. Okay. So with that in mind, and we can show quickly the applications for it. Certainly it's still a simple case. So we showed this Chapel code to calculate pi based on numerical integrations. And when we do the numerical integrations, we can always take this discretization approximations to change it to be the sum of some numbers and some arrays, something like that, right? And then when you compare this code to write this code in Chapel, it's not as difficult as you'll see or other function code. Pretty much the same simple. So the Chapel always say we have a constant of pi, the pi number there, and then we can have a configure constant. Configure constant is in Chapel is the constant the variable can be overwritten in runtime at runtime. And then we define the variables, and it's basically this the step, and then we basically one loop. You write the sum and get it done. You can do it, right? So the right and the output is one is the results, the other one is the difference between what this calculated value with that compared to that. So here, because this code is one for loop, so if you go to Chapel and you want to run it in parallel, so you can simply just change the for loop to be for all, right? And then use the reduce to do the sum. So that's only one line change. And you compare the code and you run it, and you can change it. It pretty much is the same thing, right? So this is basically say for all is the way for Chapel to do a parallel for. So I think some of you, if you are familiar with, if you use MATLAB, you know, in MATLAB, there's a part 4. I think they take the same approach and underline the philosophy is basically is like shared memory solution, like OpenMP, those type of things. Okay. And then the task statement in Chapel, the first come up with is called a begin statement. A begin statement and usually to create a dynamic tasks with an unstructured lifetime. So it's basically like the fire and the forget. So it's basically running for a while. So chamber program always start as a single main thread. And then you can start it and start the concurrent task with the begin command. So when the runtime compile and runtime set a begin statement, a task spawned by that begin statement will run in a different thread, while the main thread still continue whatever it's going to do. So if we say this piece of code, so we have a verb there, and the main thread is basically to print this line, and then we have a begin. So what in the begin, uh, this this part or this part will be executed by another thread and thread 1. And here, this code will be run by the main thread, the main code, main thread. And then when it counts another begin, and then another thread will pick up this. So like another thread work on this task. So if you compile this code and run it, and you'll find, well, the main thread and print 3 lines first, and the other come the second one. There's no order here. So that's basically the logic of Chapel and the task, the statements, and the begin, and also the following steps are called core begin. Those statements that they run is assigned chronologically. So it's not in certain order. So that means when you use this command and need to add some further controls, okay? And then the other one is called core begin. So core begin, it's something like the begin and the core begin. And the main difference we explained here, so we can talk about that is basically is almost equivalent to begin because all the writing statement run asynchronously. But if the mainstream is main difference is a low code can run until the core begin block has finished. So you can see this piece of code, and then this is the main thread will run this, and the core begin is the big lob. And the core begin here is this will run by one thread, and this will by another thread. And then this is the main thread. So you can find this main thread will print last lines because it has to wait for this part to finish. And within this part, there's no order here. Sometimes you run it, maybe the first comes first, and task 1 comes first, but when you run it, sometimes the task 2 comes first. So calls means here are different in that calling code wait for the code begins block of parallelized code to finish before continue. Okay. And then we said because they run, there's no certain orders there. So Chapel has a SYNC statement to do the synchronizations. As with other synchronization certainly will cost a little bit more, but it is there, and maybe you'll have some other ways you don't need to use it. So the keyword SYNC provide all sorts of mechanisms to synchronize tasks in chapels. So it can be applied to variable and to statement and to block of code. And we'll show it can actually apply to loop as well. So you can simply use SYSN to force the parent task to stop and wait until its spanned child task ends. So the same code just now, and because it comes with no order, if you put to add the SYNC statement here, and this will always run. This will have to wait. And if you have to do both of them, they will do the both. So you can say here output, this thread always comes first, and then the first is done, and then comes to the next one. But in this case, because this we don't have a synchronization here, this comes first and this comes last. So this is actually, so if we don't use it, and sometimes you can find you may have a different thread they're in different speed, then the output may be some of trouble at some point. So here is a demo, say load is important. So the code is still calculate pi, but this time it's not, it's different way to calculate pi. So compute the value of pi by adding up the area of many rectangles on the half of a circle and doubling that value. So this is basically in Chapel and use the procedure, and we'll have a procedure is basically like a function. It's a calculate area initial, right? And each thread will do this. And basically, the one for loop and is across all the threads, and then use begin and to calculate the area. So if we do this way, and as we showed previously, because this the main thread will comes first, and so in the case the final will be a 0 because it's initially is a 0, and then this each actually do its own sum. So in this case, the simple solution could be as simple as you put sy and c and statement and for this for loop, and basically you force all the main thread to wait until we have get this done. So in this case, you can say it fixes this sort of risk conditions, and this all comes first, and then your code will print out the right results for you, right? So this is one thing, and then the other thing, this slide I want to show, when we do computing on a cluster, we'll reserve how many CPUs, how many nodes to use. That's always very important, and particularly when you try to use Chapel, it's critical. Why? Because the Chapel run on the local is a shared memory solution. If you don't define how many threads to use, it will use all on the load. So here is the same code. If we run it on a login node this time, because it's very, very short. So I just gave it a shot. And you can find it automatically use 16 threads. So Chapel will utilize all shared memory cores on a load. So on Gram, the majority of Gram's load, the 32 CPUs per load, but it's typically 2 sockets. So each socket has 16. They are closed the shared memory in a block. So it's either you run OpenP code or a pthread code, or you run Chapel. By default, it will use 16. So when you do the code, run the real code, you need to specify how many CPUs, how many threads to use. Otherwise, it will use all of those. But for shared cluster, some nodes or some CPUs, they're used by other jobs. If you don't specify yours, you basically you force your code to run and where some other jobs are running on the node. Okay. And we continue and show for your demos and show for your examples here. So here for the task parallelism, so locality control by example. So we want to demo task parallelism here as well. So here we use a call for and cross. We can use this code to test on the same node or cross load. We call it locals in chapel. So what it does is say we call for all, is we say index for locals. And on each locals, we basically get how many CPUs on that locals. And here we'll get a number of CPUs on each locals. And then we basically you run and from the 1 to all the way go to the number of the tasks per locals, and then you can ask it to do something. So if we run this code on 2 locals, and each result for 2 CPUs, you can find it where this basically where it's 2 on this load and 2 on the other load. So you know when you do the call for all and you do the locals, you can find this code can run cross-load, and there's no problem. And if you run it on one node, and on one node it will be basically one node is only 2 CPUs available there. Okay, and then another example to demo is for the data parallelism by example. Although these all demos are from the Chapel's tutorial website. So here is basically it's a config constant. You can always overwrite it, and there's a definition of a domain. A domain is a quite important concept in your Chapel, and a domain and the domain maps, they are the key to do the data parallelisms. And the domain maps is the way for you to run data parallelism across load. Okay. So this is basically define a domain, and then you define an array, and then you can use a for or to do a local parallelism, and to do something to change the number of for each change the values for each element, and you can write it out. Then if we do this, and this basically is run on one single, we use it on one node, and on one node, each node will actually 4 CPUs whatever. And because this can overwrite it, if you 1,000, there's no way to print it, right? And then I just say, well, I use 4, it was a dimension of 4, right? So it's a 5, sorry, it's 5 by 5, and the printed numbers. So if I want to do the same thing, cross-load, and then here is basically is run the same code, is distributed and cross-load. So here in Chapels, it comes with use that the modules comes implemented in Chapel, and this one will use the cyclic dist, and it's basically cyclic distributor module. It's the simplest way to distribute the domain across cross-load, and it take the simplest round-robin way to map the index here. Okay, so the code is exactly the same, and it's basically you do like a D map, and starting from the first element, and then you do the same thing. So in this code, you can run. Actually, you can go to run, say, use 3 loads, and each has 2, and will run the same code, or you can use 2 for the same thing. So once you have this parallel code for distributed parallelism, it's ready to go, and it doesn't matter how many many node you are going to use. Okay. So I think this is the basic the main approaches or statements used in Chapel, and certainly you can use it in the rare applications, and unique example, and like Jacobi iterations, or like the heat diffusion equations, all kinds of things you can actually implement it. It's not as more difficult than C or MPI. So put it together, the last slides or last 2 slides will talk about the domain maps, and that's the key for Chapel to run cross-load is for the distributed parallel solutions. So this is basically a multi-solution feature, And you say domain maps are recipes that instruct the compiler how to map the global view of the computations. And then is basically is mapping of indices to localities, a layout of the domains arrays in memory, and the parallel iteration strategy. So the cooperations on array and the domains. So if you say this is basically this is around one node, and this is around CPUs on that node, this is on CPUs on the third node, for example. So this is basically, in principle, the chapel as well as some other HPC languages. They basically run is like a hybrid MPI and OpenMP solution. And when is on one node is run in the shared memory solution. And the Crossload certainly is a distributed solution. Okay. And then CHAP's domain map philosophy here is a chapel provide a library of standard domain maps. There's a bunch of them to support a common array implementations effortlessly. Well, let's say that. And then the user can actually add their own, write their own. Expert users can write their own domain maps in chapels to cope with any shortcomings in their standard library. So that because it's always keep going, keep adding more things, right? Chapel standard domain map are written using the end user frameworks to avoid the performance cliff between built-in and the user-defined cases. So that's pretty much I planned to cover for today. The last slide is reference. So if you want to check the details, go to Chapel's documentations, and there's all details, explanations, and the protocols, and the future want to go. And then there's an online tutorial from Chapel's homepage as well. A few slides actually, quite a few slides I basically taken from there. And there are some examples come from others. And then Computer Canada and West Grade and so our colleagues, Alex actually did the Champo tutorial at West Grade. So if you go to there, they have step-by-step explanations. I think that that tutorial is run for the full day. So there was more details and for how to actually use it. I think there the bigger thing is application is the 2D heat diffusion equations, how to implement this sequential and go to one shared solution, one node, and then it's multiple load in chip. And then there's some others as well. If you go to online, you can find a bunch. Okay, thank you. That's it.